this evening.
Thank you for the fabulous introduction. I'll go ahead and share my screen so we can get this started. All right, you should all see a cartoon here. Welcome to Mass Extinctions and the Real Jurassic Park, what California corals can teach us about today's crisis. You already heard a bunch about me, so I'll blow through this side. I'm a mass extinction researcher and I specialize in reefal ecosystems. We'll talk a lot about why we're looking at coral reefs and not just dinosaurs at these extinctions. This is the geologic timescale. And this geologic timescale is by one of my favorite artists, Ray Troll. Ray Troll is an incredibly talented artist who has a great knowledge of paleontology, and he has contributed to the energy in my classrooms greatly. So I just want to give an ode to him and also recommend that you check out some of his paleo art if you're interested. The geologic timescale is really important, and we're going to be using all of these terms tonight. Geologists read everything from the oldest to the youngest, and we'll also move through our mass extinctions like that. It's a way that we tend to talk from oldest to youngest. One thing to note about this geologic timescale, let's look at this little red box at the bottom, is that the size of these boxes are not indicative of the actual length of time. For instance, this box down here is 4 billion years. So it shows that Earth formed 4.5 billion years ago. And we call this whole time from 4.5 billion years ago until 541 million years ago. You can read it if you can see my cursor right there, the Precambrian. So 4 billion years are in that box. And then the last 541 million years are above it. And the reason we do this is that the three eras of more complex life, the Paleozoic, the Mesozoic, and the Cenozoic, are above those 4 billion years. So we will be talking about these big 5 mass extinctions. I'll go through them really quickly since we want to focus most on the one that's most related to us. Ray Troll went ahead and in his 6 extinctions geologic timescale, put in the Anthropocene or the end Holocene mass extinction at the top, preparing for it, possibly to update his art later. The first thing we need to do is simplify a bunch of things because we have a very general audience tonight, which is wonderful. So let's just take a step back and define a couple of things. A mass extinction means that more than 50% of global biodiversity is rapidly lost. We need to talk about what biodiversity is. Biodiversity is the type of life, so the variety of life. We'll use species because most people know what species are. So we have to lose like at least 50% of the types of species out there rapidly. Now, this is a funny word because when you say rapidly and you talk to a geologist, we say, oh yeah, less than 1 million years, totally rapid. So that's rapid for us. There have been 5 big mass extinctions in the geologic past, and evidence looks to show that we are entering the 6th, and we'll talk a bit about that. More art by Ray Troll. Something to note is that the serious study of mass extinctions is a relatively new field, and I cannot call on students more to action if you are interested in studying mass extinctions. This is a cutting edge field. I was lucky enough to study under Dr. George Stanley at the University of Montana, who was one of the original mass extinction researchers who looked at coral reefs. So he's a real pioneer and still doing quite a bit of research. This chart's a little confusing, but what we're looking at here are the 5 mass extinctions through geologic time. You can see it goes back 550 million years ago. These lines mean the biodiversity goes up, then it crashes down. Then it goes back up and it crashes down. It's that crash down rapidly that we're calling the mass extinction. But extinction is always occurring. Background extinctions occur all the time. And there are smaller extinction events that we don't have in this mass extinction category, like the Ice Age megafauna. Most of us know that California used to have mastodons and mammoths and saber-toothed cats running around, right? They're not here anymore. That was part of an Ice Age fauna extinction, a smaller extinction, not a mass extinction. 99% of the fossil record is extinct. That's what happened. Life evolves, other species go extinct. And I want to acknowledge the last two lectures and what has been discussed in relationship to Macaulay. So extinction means gone forever. Once a species goes extinct, it doesn't come back, it doesn't re-evolve, it doesn't suddenly appear if it, had disappeared for real. And that's very different than, say, like a localized event where you might have a great deathbed. There might have been something that happened, like a volcano erupting or a big mud flow or something that takes out a whole bunch of organisms in a region and leaves behind a deathbed. If other organisms of that same species are still wandering around somewhere else in the world, then that species isn't extinct. Now, what's going on in Macaulay? I know a lot of people are tuning in just to find out here. I can say that from what we know about these organisms, they do not seem to be related to any mass extinction. There wasn't a mass extinction during the times that they could be alive. And it looks like some of these species occur, of course, before and after the time they are found there. So it's likely a localized death event, which makes it really exciting. And I'd like you to stay tuned because we will have the age of these fossils on Friday. So hopefully that news will be released somewhere. Okay, back to extinction. Extinction means gone forever. Recovery is a word I'm going to use throughout this presentation. Recovery is the length of time, and it's always very long, it takes for biodiversity to return to its former levels. Remember that the species will never come back, but enough varieties of species will come back that you have that bulk number of amount, right? So it's the diversity of life is the recovery. You never get back the things you've lost. But sometimes a species loss is part of a mass extinction. So I put up this picture here of the California brown bear. If you don't know the California brown bear, it's on our flag. It is very much extinct. The only place you will find it is stuffed in inside glass boxes, like Mariposa here, who's in a museum. And we're likely entering a mass extinction right now, which we'll explain during this lecture. And I like to look at Mariposa, this what they named the stuffed bear, as perhaps number one. So maybe this was the beginning of our mass extinction. Who knows? But human-induced biodiversity loss is very apparent. I just like to throw this out there. If we're going to have an extinct organism on our state flag, I think it ought to be the California state dinosaur. If you didn't know yet, you have a California state dinosaur found in the Central Valley, and I think it looks fabulous on the flag. So if anyone has any flex with Governor Newsom, I think this is a great replacement. This is what California might have looked like during the time of Augie, the state dinosaur running around in the Central Valley. The coast was inland. Okay, so dinosaurs are really exciting, especially Augie. Why are we talking about reefs tonight? Reefs are keystones to biodiversity. You may have heard of a keystone species before. Think about reefal ecosystems as the keystones to the biodiversity. The reefs contain most of the life. They're indicators for every mass extinction. Different organisms built reefs. We had rootists and sponges and all kinds of things. We're talking about corals tonight to simplify things. Reefs have excellent fossil records. I mean, they're practically building a rock. So they fossilize extremely well, and they have a lot of data within them when they fossilize. We're able to get quite a bit of information about what's going on with the sea level or the water temperature, how things are doing, whether or not they're in a photic zone. So we get a lot of information from reefs that we can't get from other organisms. Now we'll do a review, and I'm going to go very quickly through this because we want to focus on one extinction specifically. A quick review of the big 6 mass extinctions, because we're going to include today like Rachel. Starting at the bottom, because we're geologists, let's go to the end Ordovician. This is what Earth looked like during the end Ordovician mass extinction 444 million years ago. There was an 86% species loss. What was going on here? Plate tectonics, always moving, sometimes causing problems for life. Here you can see that most of the big supercontinent there is over the South Pole. When a continent moves over a pole, it will glaciate. And that's exactly what happened in the end Ordovician. Most of life was still in the ocean at this point. It was just starting to crawl onto land. So this was really a marine mass extinction because we didn't have diverse life on land. Reefs completely collapsed, one group of corals to never return. I want to talk only in this presentation about supported causality of all of these extinctions. You will find theories on gamma ray bursts and supernovas and impacts that don't have global signatures, but we're just going to talk about the things that we can prove, the evidence that we have in the rock record for events large enough to cause these mass extinctions. We had this glaciation that we know. We know that we had changes in CO2, in this case, sequestration. We know that we had climate change, first a glaciation, then a melting. We know that the sea level changed. Massive sea level changes. Where are the reefs? They're in the shallow zones. We know that we had ocean anoxia. That means a lack of oxygen in the ocean. Just note that there is no catastrophic event. Plate tectonics. Let's move up. We're in the Devonian. This is what Devonian Earth looked like. 359 million years ago, a 75% species loss. Here's the late Devonian. 97% of all vertebrates go extinct. Anything over 3 feet long during this time did not make it. Reefs completely collapse. They'll rebuild in a few million years, but these big carbonate platforms that they built it took almost 100 million years for those to come back. So it was a real difficult time. Some of the things I look at, stromatoporoids, tabulate corals, they go away. So what happened during the Devonian? It wasn't glaciation. We had Siberian volcanism. Now, when I talk about volcanism at each of these mass extinctions, I'm not talking about a volcano or 10 volcanoes. I'm talking about a rip in the Earth's crust the size of countries and lava just spewing out over these big tears and volcanic outgassing that's releasing all these greenhouse gases, especially CO2, which we talk a lot about in this presentation and today. We had climate change, we had ocean anoxia, ocean acidification, sea level changes. Once again, no evidence for a global impact that would make a difference. All right, let's move up. We're in the end Permian. Here we have Pangea, the end Permian 252 million years ago, 96% loss. This is known as the Great Dying. This is the largest mass extinction of them all, and you may not have heard about it. The dinosaurs aren't here yet. This is going to clear the way for them. So what happened here? First, our hit list. We lost these really incredible forests of these seed ferns, glossopterids that used to be all over the world. 75% of insects. We lost most amphibians and reptiles. Invertebrates, things without bones, were heavily hit too. Half of the fish go away. Reefs completely collapse. Takes them a very long time to rebuild after this, even in relation to the other extinctions. Once again, we have volcanic activity like a rip the size of a country. Massive CO2 increase with all those greenhouse gases going out, climate change, sea level change, ocean acidification, and anoxia. This is just a quick snapshot of some of the cool critters we lost from the Permian mass extinction. I'd like to focus, whorl tooth sharks. What a loss, those guys are cool. No one's really sure why they had these whorls, probably to like be shell critters. But I want to stop and acknowledge the trilobites here, if you can see my mouse. You might have seen trilobites before. A lot of people have seen trilobites, make jewelry out of them. You can see them in rock shops. Maybe you found one. If you ever find a trilobite, they're such a cool index fossil because it means you're older than dinosaurs. Think about that with your trilobites next time. All right, moving up, and this is the one we're coming back to. So pay attention, end Triassic mass extinction. Here's Earth, Pangea breaking up, and Triassic 201 million years ago. 76% species loss. What happened here? We lost most of our plants. When it came to our little four-legged critters running around, 42% gone, mostly amphibians. We lost all the pseudoseuchians, mammal-like reptiles took a big hit. Marine life, our placodont's, I'll show you some pictures of these. Most of the invertebrates, and reefs completely collapsed. I look at reefs at this mass extinction because this mass extinction has the recipe that is most similar to ours today. And what was the supported causes of it? Volcanic activity. This time we call it the Central Atlantic Magmatic Province, but it's just another one of those big flood basalts, those big rips with all the lava coming out. We had a great greenhouse gas coming out of those volatiles from the magma or from the lavas, increase in CO2, climate change, ocean acidification, calcification crisis, sea level change. It's probably starting to sound pretty familiar as we go through these. And here's some of the creatures we lost, our little plankton's. Okay, let's move up to the one you've been waiting for most likely. Finally, the impact. Here we have it, the asteroid hits. This is cool. All right, so the end Cretaceous mass extinction, this is the one that kills the dinosaurs. 66 million years ago, 76% species loss. Our most famous mass extinction, not even our biggest, but it's super cool because there's this signature all over the world that shows that an asteroid hit. There's an extraterrestrial dust, layer of dust called iridium, you can find in many places around the world. And there's this giant crater off the Yucatan where the asteroid hit. So what happened here? Everything on land was hit hard. One way to look at it is, anything over 40 pounds is dead. That's pretty much what happened. You lost most of your plants. All dinosaurs go away in this. Now you notice I have a little parentheses there, non-avian. Dinosaurs, little dinosaurs with feathers that evolved to be the birds we have today, they live. So in a way, well, not in a way, very much dinosaurs are still around today. We have our avian dinosaurs that evolved into our birds. Many marine organisms were also affected. Invertebrates, ammonites. Ammonites are those coiled creatures. I'm actually wearing some ammonite earrings. I'm not sure if you can see them. Ammonites go away during this mass extinction. So that's another fun index fossil. If you're ever at a rock shop or you see some jewelry or you find one, if you find an ammonite, you know that you're at least as old as the dinosaurs. We lose our marine reptiles. Those are swimming dinosaurs. Reefs collapse. So what was going on? Well, we know there was the asteroid, but it's really important to stop here and acknowledge that things were already bad. Biodiversity was already some of the lowest it had been for certain groups. There was another one of those big lava fields that had been going off for, thousands of years. We had climate change and ocean acidification, and we had the asteroid impact. Dinosaurs never walk the earth after the asteroid impact. They just fly it as avian dinosaurs. So we know for sure catastrophic event was involved in this mass extinction. But we also had this volcanic outgassing killing these dinosaurs, right? So long, dinosaurs. Well, sorta, because dinosaurs are still around today. Some of them are doing really well in our mass extinction. This is my ode to Jeremy Jackson, who often talks about pigeons. And I would like to say, especially now that we've gone through their evolution and how they're little dinosaurs dominating the world right now, maybe they're worth acknowledging. Okay, what all these extinctions have in common? Catastrophic event wasn't necessary. We learned that. They're correlated with environmental change. All you need is environmental change. We happen to have climate change and oceanic change at every big mass extinction. And at 4 of the 5 mass extinctions, we have ocean acidification. This is a confusing chart. So just look at the big black blocks with me. I'll put my cursors over them. So this big black block is showing that at the end of each mass extinction, it takes that long for reefs, coral reefs to recover. And if you look at the bottom, this is in millions of years ago. So it takes corals millions of years to recover once they collapse. They can collapse quickly, as we are seeing today, but they cannot recover quickly. All right, so what about today? This is what you're probably waiting for, right? Talked about the dinosaurs, let's get down to business. What's going on? Ray Troll left it blank because he's a great scientist as well as artist. So what will we call it? I called it the end Holocene mass extinction. Here's Earth 2021. What % loss will we have? Let's talk about where life is to begin with. Coral reefs and rainforests. Coral reefs are less than 1% of the ocean floor, but they're home to more than 25% of the diversity of marine life, the types of things. Then think about how much of other life in the ocean relies on the coral reefs. Similarly, the rainforests. Rainforests are less than 2% of the surface of Earth, but they're about half of, about 50% of all of the species on land is found in the rainforests. Now just take a minute and think to yourself, what is the state of reefs and rainforests as we have this presentation? It's not good. Some of it is even intentional. Most of it's unintentional. We didn't mean to pollute the oceans or warm the planet, right? But most certainly, people in certain regions meant to burn down the rainforest to make room for cattle farming. And this is happening globally. We are losing our reefs and our rainforests. What we know about extinction now is we know about the rates of extinction. It is incredibly hard to quantify the loss since we didn't start counting until we were well into a downward spiral in extinction. We have not identified every species out there. We didn't start keeping track of them until recently. Once we identify threatened species, they aren't often followed up on. Maybe the big stuff if it's under law in a country, but a lot of what's going on, we don't know. So what we have to do is we have to model for the knowns. And what we know is the rate of change. We know that the extinction rate that we can watch is higher than it has ever been in a background extinction. It's not a background extinction. It is currently at least 100 times higher than a background extinction. A lot of models say that it will be at least 1,000 times higher than any background extinction rate in the future, and some of them bring it up to 10,000 times higher. This is a mass extinction. There are certain groups that we have followed that were able to watch their decline since the Industrial Revolution. We have to remember we didn't have great data to begin 150 years ago when our biodiversity started to really decline, which was Industrial Revolution, Biomedical Revolution, human population spike. So here's just looking at some things since 1970. Remember, the decline had begun for almost, for most things, over 100 years before this even begins on our chart here. But we can see the fall. And it doesn't matter if you're looking at marine life, if you're looking at freshwater species, if you're looking at terrestrial. So we're talking about the variety of life going down. It doesn't mean there aren't a lot of pigeons or there aren't a lot of people or there aren't a lot of cows, things that you see. It doesn't mean life just goes away. We're talking about the types of life declining. Something lines up pretty perfectly with this decline, and that's the human population curve. So human population curve looks like an exponential equation. It's what we call a J curve when we're talking about it in biostatistics and environmental science and stuff. So human population goes up at the same rate that extinction goes up. Pretty interesting. Something else lines up with human population, and that's CO2. As more humans come onto the earth, the CO2 also increases with that same little curve. And we've learned that carbon dioxide warms things, right? You spew a bunch out into the atmosphere, some of it goes in the ocean, some hangs in the atmosphere, it warms things up. I want you to look at the chart on the left, and I'll hold my cursor over it. So this goes back 600,000 years. To me, it's yesterday, but it didn't matter if we went back 6 million years or 600 million years. CO2 through time is constantly changing for various reasons. And in the past, CO2 has been higher than it is today. It's not the number that bothers us when we talk about mass extinction and climate change. It's not that CO2 has risen. It's the rate at which it rose that is an issue. Biodiversity can hold strong with, great changes in CO2 or other atmospheric changes, but not if it happens rapidly. It needs to happen at a rate at which things can evolve with it. And what the difference is between now and the past is the rate of change, just like our extinction difference. We don't see this rate of change, except for maybe the asteroid impact, in our past extinctions. And of course, CO2 rising temperatures. The ocean is our #1 producer of oxygen. It's also our #1 sink for carbon dioxide. So that extra CO2 that we're pumping out, it likes to go into the ocean. When it goes into the ocean, we can get ocean acidification. Now, there are some misconceptions with ocean acidification that it turns the ocean to acid or you wouldn't want to swim in it or something like that. But really, ocean acidification just means that the pH has changed a little bit and you wouldn't notice. You wouldn't notice as a person swimming in it or living by it or maybe, hanging out on it. But critters that make their shells inside the ocean, the ones that live there, they can have a calcification crisis, and it can be a very big deal, especially with corals. Oh, corals are the most finicky of the finicky. They don't like changes in anything. I'll say it over and over. They don't like changes in light. They don't like changes in temperature. They don't like changes in their waves. That's why you can't keep a true coral in a tank. I once saw like a display at the Smithsonian that sort of did. But you have to have a wave action and they have to be in a certain light, but they're especially sensitive to changes in temperature and changes in pH, which is why they're the alarm bells. And they have been ringing for a long time. For decades, they've been trying to tell us something that we can see in the fossil record. You may have seen headlines about this. It's recently come into popular press as something of interest. If you haven't, it's not your fault. People weren't looking at it until fairly recently. But coral reefs are in trouble. And there are things called coral bleaching events, especially as water warms. Corals don't like rapid changes in water temperature. Again, rates of change. They don't like it when it quickly warms up. When it quickly warms up, one of the things they will do is commit suicide. They basically starve themselves of their symbiotic algae and they bleach. Most bleached corals die. Some of them don't, but most of them do. So you may hear about bleaching events going on across the globe. This isn't news to scientists who study corals, past corals, present corals. This is the International Coral Reef Symposium. These are just a few of the things that went on. Unfortunately, I missed 2020. I was supposed to present there, but this is a team of hundreds to thousands of people who get together, who study coral reefs. And it was a decade ago that they signed a consensus that the Great Barrier Reef was bleached to a point of no return by 2020 at the rate at which things were going. And things got worse. So coral reef researchers have been watching corals like this for a very long time. I highly recommend this Netflix documentary. I'm going to say that again because I think it matters. Netflix documentary. So it's exciting. Not that Ken Burns isn't for something like that, but it's a Netflix film. So you can watch this. You can watch this with a variety of people, and it will keep them entertained. And it's fascinating. This is about some scientists documenting some corals, and it does a great job presenting the science without giving any false hopes. One of the things that the researchers in Chasing Coral ask the public to take away with them is that losing the barrier reef should mean something. They don't say that the barrier reef is going to remain a barrier reef. It's not going to be this biggest, largest living thing on Earth, even if there are pockets of corals that are alive. And what they really stress is that this death should be our wake-up call. And what corals are trying to tell us should now be listened to. So I highly recommend it. And it's not too depressing, I promise. It's not Seaspiracy. So let's now look at our fossils that we have in California, Nevada, Alaska, and Mexico, and how they relate to our sixth extinction. No catastrophic event. Remember, we're hopping back to that end Triassic mass extinction, smack dab in the middle of dinosaur time. Finally, I show you a picture where you can see when I'm talking about these rips in the Earth's crust. So I'm going to point out this biggest one here. This is the Central Atlantic Magmatic Province. This is the volcanic outgassing. This is the lava field that's occurring during the time of this extinction that's most similar to our own. That's pretty impressive. So that amount of lava is our amount of emissions, right? I mean, that paper hasn't been written, but sort of, So you had this volcanic outgassing from that big rip right there, that one that hanging out. You had this increase in CO2, ocean acidification, climate change, sea level change, reefs are collapsing. Does this sound familiar? It's a very familiar recipe to what's going on now. So what I like to do is go out and check out what the corals have to tell us about this extinction. And I'm looking at Western North America. because it is incredibly understudied, especially in the recovery side. Everybody's super interested in why the extinctions happened, but not a lot of people have gone to the other side of the extinction to figure out who's there, why they're there, how long it takes for biodiversity to return, who the first characters are. And so it was fairly easy to find new fossils, new sites, new data that hadn't been looked at before. So this is what Earth was like during that Triassic-Jurassic boundary. This is your real Jurassic Park. Notice where we would be. Here's California in the ocean. We're the sea. Nevada, the coastline. And each place I went to look at the recovery of this extinction and to try to find corals, I found corals that hadn't been studied, new data that was, part of this incredible record of this extinction that might be like our own. Found them in Sonora, Mexico, in Death Valley in California, in Mina, Nevada, and Seldovia, Alaska, and near the Parks Highway, because it's not really a place, or near the Glen Highway in Alaska. So Triassic Nevada, first let's go before the extinction. Here's a picture of Dr. Stanley too, my dissertation advisor. So if we're in the Triassic side, this is when reefs are doing really great. We have to reach that boundary to get to the mass extinction on that geologic timescale. Reefs are doing so well that on this one field trip we took out here where you can see this white truck, the truck actually bottomed out on a giant boulder and I had to pull out the truck with my car. And we pull out the truck and underneath it was a giant hunk of corals. There are so many coral fossils on the Triassic side. There was a reefal maximum in the Triassic. Reefs were flourishing. They are high in biodiversity. They're much like they were today. So that was before the extinction. Then the extinction hits and we see the same cast of characters over and over again after the extinction. We see ammonites and bivalves and snails and the same thing. The reefs are gone. The reefs have completely disappeared from the fossil record. But what we did find when we kept looking is the very first appearance. We had to figure out how far you go into the Jurassic, how much further you have to move in time before you find the first corals. We found the first corals in North America that appear after this mass extinction. Actually, every place we looked, we kept finding more of them. And they all have a very similar story to tell. Here's a little picture of these corals. You might notice they're all by themselves. They're not wrapped up with other corals growing out like trees, like you would expect to see in a reef. Here's a picture from Seldovia, Alaska. This was just a couple months ago, looking for some Jurassic corals. Here's a picture from Death Valley, brand new, probably the earliest Jurassic corals. We have not yet collected, we're working on our permit, but they have some collection. So what did these corals have to say? Was it great news about what the future of our reefs will be? Since we have these, scientists and this consensus and we're able to definitely track in lifetime what's going on with our reef collapse today. Here's those corals close up again. What we found was that it took 2 million years for the first corals to appear. And we were excited, 2 million years, that's it. Took 2 million years for the corals to come back in North America. And when they came back, they weren't building reefs. These are actually really simple solitary corals that were probably living even below the photic zone. And they were smothered in a mud and they would regrow and they're kind of smothered, hiding out in the mud and not even with the sun, maybe not even with a symbiotic algae. And it would actually take 20 million years for the biodiversity of the reefs to return, for the coral reefs to rebuild, and for biodiversity to reach its former level in our most similar mass extinction. So this leads me to, what about the future? What does this tell us about today? And I like to put up this really sad picture of a post-fire zone, because I think that there is, a false idea that you have to look out your window and see an apocalyptic landscape to be in a mass extinction. That's not how it works. Maybe when the asteroid hit, yeah, I would not expect something good out my window wherever I lived in the world if an asteroid hit. That was the size of the one for the KPG. What we have today, we have human population experiment. So this is nature's first experiment since the stromatolites, that's the slime that dominated the sea, in overpopulation. So we have humans growing at a rate at which other organisms have not had without immediately dropping. This is called the J curve. So we have this J curve, and normally when there's a J curve, there's a swift drop. It doesn't work. You reach a capacity and then you fall. But we haven't fallen yet. And the projection is that we will go higher. I can remember when I was a little kid, my dad would say the population was going to level out at like, or he said when he was younger, the population was going to level out at like 5 billion people. And then when I was in college, it was the population's going to level out at 7 billion people. And now I'm teaching out of a textbook that says the population's going to level out at 11 billion people. It just keeps growing. Let's put it in perspective for biodiversity. Let's look at the number of humans. It took 200,000 years, that's how long our species has been here, for humans to reach 3 billion in number. It only took 40 years for the next 3 billion. We are exponentially growing on this planet. And according to most researchers, we have hit our capacity, yet we continue to grow and we continue to consume and increase our consumptions. There's this idea about this false apocalypse that you have to look out your window and it has to look like Waterworld or Mad Max or Burning Man, right? That you have to look out there and you have to see it in order to be in this mass extinction. But that's not how it works. Mass extinctions are losses of biodiversity. And the question is really, are you going to notice it? And that depends on your fortune of where you were born in the world and how long you live. According to my environmental science textbook, 3 million people a week move to megacities. Megacities are the future. 40% of Earth's surface is human modified. That's pretty impressive considering Antarctica is very hard to modify. So, I mean, with not that much landscape, we did a good job in 150 years of, our technology. And we lose things every day at a rate at which we don't see in the fossil record. So just some charts here. Every 20 minutes, the world adds 3,500 humans and loses one or more species. So we do have the things that we can quantify for now. And we know that this rate of increase is increasing. It is not slowing down and it is not steady. We continue to increase quickly. So the question isn't, when is the extinction or something like that? It's, will you notice? If you live in a suburban community, if you live in a city, if you live in Lake Tahoe, where I live in Tahoe, will you notice looking out your window that you're in a mass extinction? Maybe not in your lifetime. You might notice that you don't see mountain chickadees anymore and you only see pigeons and, warblers or something. You might notice little things. You might notice that, wow, I haven't seen, that kind of organism that I used to see when I would go hiking. I used to see these things and I no longer see them. But if you're living in a city, you might be like, wow, pigeons are populous. Life might not look different for everyone, for the privileged part of the world that isn't on the front line. These are the faces of your mass extinction. There's people, lots of people and lots of pigeons. We are doing fine right now. What is going to happen is an entirely other presentation when we talk about carrying capacity of Earth and our lifestyles and our consumption and the projections for future population numbers, or even keeping them where we're at right now. So that's a whole other presentation. And then we're selecting for certain species to live, right? We're selecting for things we eat. We're selecting for cows. Oh, I put puppies in here to make everyone feel better. If you're feeling depressed right now, just look at the puppies. We're selecting for puppies, right? We keep the dogs around. And then there are other organisms that are just really, really, really great generalists. Generalists versus specialists. Specialists don't make it through mass extinctions. We're specialists. But the generalists, a lot of them do, like jellyfish, cockroaches, dandelions. There's some great ideas about who will take over the Earth in the future, and generalists tend to survive. This is where it really becomes an environmental justice issue. And this is a whole other presentation in itself, but there are people who live in reefs and rainforests and less than a meter above sea level who are affected by this now and who have been affected by this, for decades. And so a mass extinction, a biodiversity loss, the climate change, the changes in CO2 have been noticed by other communities. Unfortunately, it happens to be in developing nations, in places, sea level change may affect more, but people who are relying on the reefs to feed them, people who are relying on the rainforests to survive, those people are the ones who are the most affected currently. Now, will that change in the future as the global impact spreads? So this is my call to future paleontologists. This is an important thing to study. It is so important. And for our most similar mass extinction all across Western North America, there are so many sites that need to be explored. So if you're at all interested in this, reach out to me. I mean, we have this early indicator of our modern corals sounding this alarm, begging us to listen. And we have this rock record that might teach us something about it. So I really invite students to reach out, or anyone who's interested, citizen scientists, anyone who wants to go out in the field with me to look for these fossils is welcome to come. So in the end, what does this all mean? This was a lot of information for a general presentation. What do we take from it? What should we take away? I'll tell you what I take away at the end of the day so that I can sleep at night because it doesn't look good. I take away that they will rise again. Those dinosaurs, those birds, those pigeons that live in the places that humans modify, they love a freeway, right? Pigeons like freeway overpasses, so the dinosaurs will rise. And that is the end of my presentation. If we have time for questions.
That's great. Thank you so much, Montana. I'm sure you can virtually hear the virtual roar of applause that is coming through Zoom. Thank you so much for this really informative presentation. Folks have been asking lots of great questions in the chat, and if there are more questions, please add to that list. But already there's some great ones, and so I'll kick it off with a really interesting question. What are some traits of species that put them more at risk of mass extinction events? And then on the flip side, are there traits that make species or communities more resistant to mass extinction events?
Absolutely. And this makes me think so much about Dr. Stanley. I wish he was here tonight. Generalists versus specialists. So if you have time to Google that, Google that. A generalist is a species that you can pick it up and you can drop it off pretty much anywhere in the world, and it's going to find a way to live. A specialist is a species that needs super specific environment to survive. Specialists, we are specialists. So we can't, we can't live without our extreme environment clothing in the Arctic. We can't live without a very specific oxygen, a very specific atmosphere. We need water, a specific amount of water. We're super, super specialized creatures. And people tend to think because we build lots of things and we've modified landscapes that we're generalists, but we absolutely are not. But go ahead and look up generalists versus specialists and check out organisms that survived in vacuums in space.
All kinds of fun Googling.
Yeah.
So then would you say that reefs are successful or not successful with extinctions because they've gone through multiple extinctions, but also come through in recovery periods as well? Are they like the canary in the coal mine, or?
Yeah, they are. That's a great example. So they are kind of the canary in the coal mine. Reefs come back. And we didn't, this presentation, we didn't have time to talk about all the different cool organisms that build reefs. Reefs do come back. It takes so long for them to come back, though. I mean, you're just talking about a very, very specific environment. You're talking about a specific oceanic landscape. You need that warm, shallow sea. And if the sea is constantly changing, no chance. So you need the stabilization to occur. So as long as things are drastically changing, you're not going to have it. So you need that stabilization. Reefs will come back. It's whether or not the intrinsic value for humans was there. You know, if we lose the big reefs in our lifetime, what is lost, you know?
Right.
But
And then
give it 20 million years.
yeah, we got time, right? When you're thinking about when we're thinking about the reefs that went extinct in the deep past, did specific species actually recover, or did they have to kind of like re-evolve in order to bring back reefs?
Great question. And you know, all the new species that I have, I'm trying to do the taxonomy on them right now. We don't know what they're related to, because nobody wants to work in the early recovery part. So I've been spending years trying to figure out what these corals are, who they're related to, where they came from. But to answer the question quickly, groups of corals go away and are never seen again. Rugose corals, tabulate corals, gone. So, and something new comes about, some new type of coral. So it's an evolution of that which survives. Could we get to a point where there are no longer corals? Absolutely. Something else may build a reef. But we could lose all groups of corals. It's possible.
Wow, that's overwhelming to think about. When you're thinking about the extinctions and you compared them to background extinction, can you say a little bit about how that's determined, and is a background extinction for a single organism or a environment, or tell us a little bit more about background extinction?
Great. Yeah. So there's all different kinds of background extinctions, but we're talking about groups. So it's not just going to be one thing. Maybe, you know, a bunch of marine families or something like that. But it's similar to a mass extinction, but at a lower rate. So you might have as much variety, but it's, you know, 5% hit or something like that. Or it might be half of all marine families or half of all fish or something like that. So it's always different, but it goes on constantly through the background.
Okay, so can you give us like a scale, like the kind of time scale that you were talking about for these mass extinctions was really short, but we're also talking about geologic time, so it's always hard to know what you really mean by short and long. Can you
So
give us some scale?
Yeah, what we have seen in 150 years is what you see in 150,000 years in the fossil record. So that's probably the best way to say it, with the exception of an asteroid impact. And most of these we don't have time for it, but most of these mass extinctions had waves. It wasn't just one down, it was wave after wave, 2 waves, 3 waves, you know, in the mass extinction that were slowly taking biodiversity down, but we're going straight for it. So
go big or go home, right?
Yeah, we're number one.
Yeah.
Well, maybe we'll see.
Yeah. When you were talking about some of the past extinctions, you mentioned ocean anoxia. How is that detected in the deep past?
In the fossil record? Oh, that's a great question. You're actually looking at rocks when you determine if the oceans were anoxic. I don't particularly study that, but if anybody else wants to answer that, they can feel free to. Yeah, it's a great question.
Okay, so we're seeing changes in the types of rocks that are consistent with anoxic conditions.
Yeah, absolutely. We can tell if rocks are in an anoxic environment by their color, but somebody who studies, you know, widespread deep ocean anoxia may be using other technologies as well. But you know, when you look at certain rocks, it's anoxic. Yeah.
Yeah, this is outside my realm too, but probably minerals that have metals in them in different oxidation states or something.
Yeah.
Don't quote me on that. That's outside my expertise. Okay. So then you mentioned some kind of startling modern issues, including at the Great Barrier Reef. And you mentioned the prediction that I think you might have said that by 2020, they thought that bleaching would be pretty thorough there. Can you update us? You know, we're past 2020 now.
Yeah.
What's our status?
And absolutely. So the barrier reef is, a barrier reef is there are all these different types of reefs. When you get into reef research, it gets super, super complex, right? Okay, so we're gonna have all these different types of reef. When we're in a barrier reef, they're very unique. They're these big, you know, platforms. This one happens to be like as long as a continent. It's considered the largest living thing on Earth. It's experienced enough bleaching events and enough death to patchwork it to a point where it will no longer be the single big reef. The best thing to do is to watch Chasing Coral, because they're going to focus on the Great Barrier Reef. And they'll do it in a really friendly way. You can also go to the ICRS, keeps all of their journals and or all of their volumes online, and you can also look at that. But it didn't get better. It actually was markedly worse than I thought it would be. It doesn't mean that there aren't places you can go and see life on what, you know, is the platform of the Great Barrier Reef, but it itself is a dying barrier reef.
So it'll transition from the Great Barrier to more patchy kinds of reefs. Is that a way to think about it?
Yeah, it's more like a little patchwork. Maybe we'll bioengineer some sections that people snorkel over and stuff like that. But
right,
yeah, it's as itself as a big platform, no longer sustainable as is, especially as conditions continue to warm instead of cool. So it didn't stabilize it. And places they didn't expect to bleach ended up bleaching and dying, also dying after the bleach. So.
Okay, wow, all right. Well, I wonder if you could share with us some of your pathway into paleontology and ancient reef systems. We often have students and even you know, pre-university age folks on these talks, and maybe you could tell us a little bit about your pathway.
Sure. And it's a different one. You know, I wasn't 8 years old and saying I was going to be a paleontologist. And that is a lot of people's narrative. That's their story. You know, they knew when they were young, but I wanted to be a writer, and I worked as a writer, and I wanted to be a science writer. So I made sure I got a bachelor's in geology and a bachelor's in journalism. And I worked in outdoor writing and science writing. And I took a course when I was working on my master's in science journalism on mass extinctions. And it was kind of like a long version of this lecture. And I just took it for fun, and it just changed my life. I couldn't believe we weren't talking about this. And it was taught by Dr. Stanley, and I went immediately to him, and I said I wanted to study this. I didn't want to interview scientists anymore. I wanted to be part of it because I thought it was important. It also happens to be extremely exciting, and I field work, which I live for. I live for being in the field. So there's that too. But I mean, you can have new dreams, you can have new careers, you can have multiple careers. I don't think the future is very narrow. It's interdisciplinary. So, you know, double major, take classes that just seem interesting. And I think it was the best move ever. And I feel like I'm doing something important. And I think that they complement each other, being able to communicate and write and being able to understand the science as well.
That's great. Thank you, Montana. We really appreciate you being here, and we appreciate your talk. Thank you again for all this wonderful information, and we sure appreciate it. So I'll turn it over to Marcia now, and thank you all again.
And thank you, Dr. Hodges and Dr. Teasdale. And I'm just going to interject, even though it's not my responsibility, on the question of ocean anoxia. Dr. Shapiro did answer up early in the chat, loads of sulfides in rocks are an indication of anoxia. So you were spot on, Rachel, too. Okay, and I want to express thanks for all of us, for Dr. Hodges, illuminating and inspiring. And I really learned a lot myself, and I think it really has helped us understand geologic time and our challenges with the current mass extinction. And to all of you, we'll see you again next week for our final lecture of this series with Dr. Neil Kelly from Vanderbilt University, who will talk about Triassic marine reptiles in our region. And just another reminder that these talks are archived on the Gateway website, so please share with your friends and family. And remember, if you have not visited the Gateway, there is great science going on. A good way to keep up with new findings in the Paleo exhibit, the Miocene Zoo, is to purchase an annual membership so you can come back frequently and keep up with the new identifications and ongoing work. So we will see you next week.